The ideal gas law. We have been talking about the ideal gas or the real gas for so long, but now we come at a unique equation as related to the ideal gases. Now, the ideal gas law takes all the three equations, Boyle's law, Charles' law, as well as Avogadro's law, into consideration. And here is that equation: PV equals nRT, where P stands for pressure, V for volume, and for the number of moles. R is something that we haven't seen so far. It's called the gas constant, which we will look at in a few minutes. And T is the temperature in Kelvin. What's unique about the ideal gas law compared to the other equations is that we use the ideal gas law not in two different states, as in we change the pressure from Pi to Pf, or Vi volume from Vi to Vf, or so on. If you remember, all the other equations were of that form, where we had, for example, Boyle's law was Pi times Vi equals Pf over Vf, or Charles' law was Vf over Vi over Tf equals Vf over Tf. But when we look at ideal gas law, we are looking at just the four variables together with the gas constant R. What is the value of the gas constant? We can actually find out the value ourselves, but it's a value of 0.0821 liter atmosphere divided by mole Kelvin. Now you can rearrange this equation to say R equals PV over NT, and then you can plug in the numbers. Think about the standard temperature and pressure. At standard temperature and pressure, P is 1 atmosphere, V is 22.4 liters, N is 1 mole, and T is 273 Kelvin. When you plug all four in, you can find out the value of R, which will equal to this number with these four units. These four fundamental units combined to give you a derived unit. Right, so here is the problem: demonstrate molar volume of oxygen gas at STP. So we solve for the volume V, and we have the gas constant now here, the number of moles, which is because it says 1 mole, 1 molar volume means for 1 mole. Temperature is 273 Kelvin because it's standard temperature, and pressure is 1 atmosphere because again it's standard pressure. When we solve for all of that, we get 22.4 liters, as we would expect. Here are a bunch of other problems that you should try to solve for. What is the volume of gas occupied by 5 grams of methane at 25 degrees Celsius and 1 atmosphere? In order to solve this problem, you will first have to convert your grams of methane to moles of methane. And you will have to convert your temperature from degrees Celsius to Kelvin. And you have the pressure as it is. Use the value of R given to you previously here as 0.0821 liter atmosphere mole Kelvin, and you can then solve for volume. What is the mass of nitrogen required to occupy 3.0 liters at 100 degrees Celsius and 700 millimeter mercury? So now you are solving for the mass. The ideal gas law will not give you the mass, but it will give you the number of moles. Once you have the number of moles, you can find the mass using the molar mass of nitrogen, which is about 28 grams per mole. Your volume is 3 liters. Temperature is 100 degrees Celsius, which you will have to convert to Kelvin. And 700 millimeter mercury will have to be converted to atmospheres. 1 atmosphere equals 760 millimeter mercury. So use that as a conversion factor to find out how many atmospheres is equal to 700 millimeter mercury.